Hello there. In this video we're going to have a little bit of fun with the field axioms. In the last video we learned that the complex numbers are a field and what that means, and here we are playing around a little bit with these axioms to get used to them, or to get used to how to actually use them. First exercise, we look at an alternative definition of a multiplication on R2. So I shouldn't call it the complex numbers because this won't lead to the complex numbers. The most natural definition would be I take a vector and another vector and I simply multiply the entries, the first component and the second component. Then again I get a vector in R2, so this definitely is a binary operation on R2. So maybe this is another field. Not the complex numbers, but another field with a much more natural multiplication. First of all, we try to find the neutral element with respect to this multiplication. I call it 1 sub star. Of course, this must be the vector with the entries 1, 1. The only possibility to leave this vector unaltered when multiplying with the neutral element is if I have 1 and 1 here, because then here I have a times 1, b times 1, which is exactly ab. Or maybe this is a neutral element. Later on we're going to prove that automatically then it's unique. We don't need to worry about uniqueness. So far so good. We have a multiplication, we have a neutral element. But now something bad happens. This vector here, which is obviously not the 0 vector, 0, 0, which I denote by 0 sub c, this has no multiplicative inverse, thereby contradicting field axiom M3. And so we see that this cannot give us another field structure on R2. Why is that? Well, I would have to find an element that when multiplying it with this element gives me the neutral element of the multiplication, so 1, 1. But down here we have a 0 times d here, which is 0, so this can never be 1, 1, no matter what c is. So this is an easy contradiction to the field axiom, which tells us that there must always be multiplicative inverses for every field element that is not equal to 0. So this will give you a so-called ring structure on R2, but we are lacking the inverses. We cannot do everything we can do in a field, meaning solving equations x times y equals something else. We can't always solve these equations here. Another way to see that this can't be a field is the following. Here we have so-called zero divisors. Those are elements that are not equal to 0, but their product is 0. And obviously, if I take here this product, I end up with 1 times 0, 0 times 1, so 0 times 0. And now it's easy to see that in any field this can't happen. So if I take any field k, it doesn't have to be the complex numbers, take two elements z times w and know that their product is 0, the neutral element of addition, I can multiply both sides of this equation by the inverse of w. So important, I have two field elements that are not equal to 0, then I know that they have a multiplicative inverse by field axiom M3. So we have this. Now it's easy to see that 0 times any element always stays 0. Actually, we're going to prove that in general over there, but for the moment let's assume that this is true. Here, by associativity of the multiplication, another field axiom that we're using, I can move the brackets, and here we have 1, because this is the multiplicative inverse. So it follows that z times 1, which of course is z, is 0, but we started with the assumption that both elements are not 0. This shows in general that in a field I can't have 0 divisors. So this would be another possibility to see that this here yields no field structure on R2. But of course this is much more direct. So now for some very nice abstract nonsense. And these exercises, they were absolutely killing me when I started to study math. I just couldn't wrap my brain around it, how to do that. If you've seen the tricks or get used to them, it's kind of trivial, but this is really hard in my opinion if you're a beginner. So if you see this for the first time, I'll challenge you to stop, to pause the video and try to do this on your own. Okay, K is any field, not necessarily the real numbers or the complex numbers, simply a set with two operations, plus and dot, addition and multiplication, so that the field axioms, the long list of field axioms from the last video are satisfied, and we're using these field axioms now to prove somewhat obvious statements, but which in my opinion are still hard to prove if you're a beginner. First of all, I claim that the neutral element of addition is unique. So if you have found one candidate for a neutral element, you already know this is the one. There's no other element. And the proof goes like that. Assume that 0 prime is another neutral element with respect to addition. Then we have the following. 0 prime is of course 0 prime plus 0, because 0 is a neutral element of addition, which means exactly that. But now, since 0 prime is also assumed to be a neutral element, this is exactly 0, because adding 0 prime doesn't change this element here. And we're done. So we have proven that 0 prime is equal to 0. But already this is I think a brilliant idea that you need to have, which wasn't apparent to me when I first tried to do it. In the same way, but a bit more complicated, is the proof that the additive inverse is unique. And this in the end satisfies that we say minus a is the additive inverse, the negative element of a. So we take an arbitrary element of our field, and b is a inverse with respect to addition, meaning that a plus b is 0, and of course b plus a is 0 because addition is commutative. Now I take another element that satisfies the same relation, and we need to show that b prime is equal to b. So let's start. Here we go. B prime. Well, the only chance I have is to bring the 0 into play. So I can write this as b prime plus 0, because 0 is the neutral element. But now I know that this holds. So this here, okay, here I have used this. 0 can be written as a plus b. Now, by associativity of addition, I can move here the brackets and now I have b prime plus a, but this is 0. Because of commutativity I can change the order, so b prime plus a is also 0, so I have 0 plus b, which is b, so in the end I have shown that b prime is equal to b. If you see it like that, you can say, well, this is obvious, but would you have thought of this? I sure didn't in the beginning. So this is the proof that the neutral element with respect to addition is unique, and that inverses are unique, as I said, justifying this notation that we write minus a for the unique additive inverse. The same, of course, holds true for the 1, the neutral element of multiplication. and for the multiplicative inverse. If you're a beginner, please pause the video and prove it. The 1 is unique and multiplicative inverses are unique, justifying this notation for writing a to the power of -1, or if you want to 1 over a for the inverse, but only after you have proven that it's unique. So, to conclude, an exercise that can absolutely drive you crazy, because a times 0, so k again is any field, you need to prove that for any other element of k, a times 0 is 0. So if I multiply any element by the neutral element of addition, I end up with a neutral element of addition. We use it all the time, it's obvious, but how can we prove this? We only have the field axioms. Now, 0 is connected with the additive structure. It's the neutral element for addition. Here we have multiplication. The only axiom that connects those two is the distributive law. So we definitely need to use that. And of course we need to use that 0 is the neutral element of addition. We do it like that. We write 0 as 0 plus 0, neutral element of addition. And now comes the distributive law, or axiom, however you wish to call it. This is the same as a times 0 plus a times 0. Now we have this equation here. A times 0 is a times 0 plus a times 0. This is an element of our field, so we know it has a unique doesn't matter, but it has an additive inverse, minus a times 0. If I add this on both sides, here I end up with 0, because this guy minus itself is 0, that's the definition. And there I end up with 0 times a, because these two cancel. And then we have what we wanted. A times 0 is 0, here from right to left. Of course, if you see each step, it's almost trivial, but you need to have this idea that you do that and that you need to use the distributive law because it connects plus and multiplication. Okay, now this crazy little exercise. You need to prove that -1 times -1 is the same as +1. You use it since kindergarten, but why is this so? This holds true in any field. Okay, now for the proof of this mean little relation. Again, -1 is the additive inverse. So we have the additive structure, but here is the product of those two. Well, why not use this little relation that we have just proven? So I know that 0 is definitely 0 times -1. So I already have my -1 in here. And now I can write 0 by definition as -1 plus 1, or 1 plus -1, doesn't matter. And now I can use the distributive law again, because it connects multiplication and addition. At some point I need to use the distributive law. So this gives me -1 times -1 plus 1 times -1, but 1 times -1 simply is -1. So now this tells me that this guy here is the additive inverse of -1. But the number 1 already is an element with this property, because 1 minus 1 is 0. So by uniqueness of additive inverses, it follows that this here must already be the additive inverse of -1, which is the number 1. So this is pretty intricate. So it's not enough to do this calculation, but you also need here this argument. Alternatively, you could say, well, I have this equation. If I add the number 1 on both sides, I do not alter the equation, it still holds true, and then I have 1 here, minus 1 and plus 1 cancels using associativity of addition, and then again you end up with this here equals 1. Okay, in the same way you can prove this. We start using this equation. 0 is 0 times a. This can be written as 1 minus 1 times a. Now again I use the distributive law and end up with 1 times a minus 1 times a, or better, plus minus 1 times a. So this here maybe I should write as 1 plus minus 1. This is very, very tedious because we're so used to these rules that it's really hard to remember which axiom did we use and which thing seems obvious to us but is actually not justified yet. Okay, and this here is of course a plus minus 1 times a. Now if you have a look at this, here this says that this guy is the additive inverse of a, because a plus this number is 0. Again, because additive inverses are unique, it follows that this here must be minus a, because minus a is a inverse, additive inverse. Okay, again, please justify this step. Okay, and finally we prove the general rule of signs that minus times minus equals plus. Now, using all this is not so hard anymore. We have minus a times minus b equals what we just proved. This is the same as that. Now by associativity I can drop those brackets here because the order of the multiplication doesn't matter. Now because multiplication is commutative, I can pull this minus here up in front, and then we use b and we are done. Okay, this is not so hard, but this here I think is really hard. Especially here, you need really to use the field axioms and what follows from them. Uniqueness of inverses to actually prove this in general. Okay, if your first reaction was, what the hell just happened, you're in good company. I felt the same way in the beginning. If you're studying algebra at university level, you quickly get used to abstract nonsense like that, and it's not as bad as it seems for a beginner, but in the beginning, it really did cost me a lot of nerves. Okay, if you watched till the end, great respect. Thanks for watching, and hopefully I'll see you soon.